He looked like really. And he started like pacing around, a little like circle area that came off. He just pacing around like in the middle of the lecture. Dan said he couldn't take it no more.
It was baby I thought and then he walking around. Alto was sitting behind
That
us.
was the day that Alto was. She makes some. They're just like sprinted to where we were sitting next to where Alto was and just snatched it in the bag.
Whatever some exam questions.
He did 3.5, so I assume it was.
They talked about like some new.
We
should find versus usually. There might be some.
But I don't think it's like anything.
I don't know if Boston wants to see that was last day was funny. Yeah, it's Josh. Yeah. Where's my crown?
You're not the latest.
If I was a legit, I would not be. I don't know how could they just bring and doing that. And still able to get it. It is big.
They're still hard. They're hard to. They got a color inside wise.
Sorry. I give it, yep, absolutely.
Yeah. Also alcohol.
There's another.
Oh, he's different. He's studying. But you are out. You like general brain. You like general brain. It's like it's whiskey alcohol, but it's similar. You know, get a different breaks. You know what my son's.
Alrighty, it's 5 o'clock. We'll get started. How are we doing today, everyone? Good. Okay. How do you feel about the exam? Not good. Cool. Okay. Well, hopefully after this, you're feeling at least a little bit better. I know that usually when I do this on the weekend, we tend to go over the mock exam. I feel like mostly. Is that something we want to do today? Kind of go over those questions, or are there specific questions we want to ask me first, and then that ties into a mock exam question? We can kind of see that. Mock exam, yeah. Do we kind of just want to go through it, or do you have specific questions from that one? Go through it, absolutely. Okay, so one thing with your mock exam and just your exam in general, she does include the periodic table at the very end, as well as your formula sheet. I think when you're studying for an exam, especially for your final, your formula sheet is going to be very important to see like what equations you know, what concepts relate to each equation, and then just kind of gets you a idea of what's given to you, and then you can then you don't have to memorize as many things. So one thing I like to point out here is that you do get your rate law equation. I don't think you get it for zeroth order, but it looks very similar to your second order. It just has a minus KT, and it's obviously not the inverse of them. Okay, but in terms of this chapter that we're talking about, or this exam, I don't even remember what chapter 8 is. Molecular sources, yes, IMF and all that stuff. So that's not really any equations, but your calorimetry is these Q equations here. And then that has to deal with your CH2O. Your enthalpy and entropy and all that fun stuff there, delta G free energy is all in this section right here. And then this is your kinetics that you have. Okay, so the bottom half of your formula sheet should be where you're going to spend most of your time for any equations you might have. Any questions on the formula sheet or what's given to you on the formula sheet? Okay, what does this apply to here? Yep, this is first order. What is this one? Awesome. And then, does anyone remember what this one is? Yep, this is your activation energy. So if you're finding two different kinetics or two different rate constants, it is going to be based off of this equation here. And what is the rate constant affected by? Just temperature. And that's why you have your temperature components of your equation right here. Okay. So that's also a really good spot to look at. You can kind of see what is affected and what affects that constant you're looking at based off the equations. Alrighty, we can start with the mock exam then. Okay, so for, I guess, yeah, we'll start with it. We'll just go through it. So for question number 1, we have suppose the 3 unknown pure substance are liquid at room temperature. You make vapor pressure measurements and find that substance Q has a pressure of 110 torr, substance R has a pressure of 42 torr, and substance S has a pressure of 330 torr. Which substance has the lowest boiling point? Does anyone know what answer this is? S, do we all agree with S? Why do we think that it's S? Yeah, awesome, right? So I guess so the higher the pressure here, the partial pressure, means that it has an easier time being boiled off, right? If something is easily boiled, it doesn't take as much effort to boil it off. Something that might have a harder time boiling might be water in comparison to something like methanol, I think has a lower boiling point. But in any case, the higher the pressure, lower the boiling point. And what can we say about substance S? Do we think it has strong or weak intermolecular forces? Why do we say weak? Easier to boil off, right? The lower the boiling point, the weaker those IMFs are. And again, it has an easier time getting into that gaseous phase. You don't need to put as much effort in to get it through its phase changes to the gaseous phase, excuse me. And so therefore IMFs are weaker. Okay, one thing I like to point out when you're giving a multiple choice question, if you're asked for like which one's the most or which one's the least, it'll never be the one in the middle. Never the one in the middle. So you can always eliminate that. And if it's asking for most or least, often not going to be all the same, but just as a heads up. Any questions on 1? Okay. For question 2, we have in the phase diagram to the right, segment blank corresponds to the boiling point of a substance. Okay, so before we even answer this question, what is this section here? That's going to be a solid. What's going to be this one here? Awesome. And what's your bottom section?
Yes.
Awesome. What are our lines called?
A and B.
Yes, and what do we call vaporization? Awesome, phase changes, right? All of our going to be a phase change. Okay, so we said that A to B was vaporization, and that's going from, awesome, right? So from liquid to gas, we're vaporizing. What do we do if we go from gas to liquid? Condensation. What is this AD segment here? Yep, melting, or what's the reverse? Freezing. And then what's our AC line? Sublimation or deposition. Awesome. Okay, but all of those will be a phase change. What do we call point A? It's going to be our triple point. I don't think we talked about B. Does anyone know what B is called? I don't think we talked about it. Yeah, this is called your critical point. I can't remember if we covered it. Okay, and so how I remember your solid, liquid, and gas sections of this, your high pressure and low temperature is going to be a solid, right? We want anything under high pressure is not going to act like a gas because you can think of that your volume is going to be very, very small. So you're going to condense it. So that's going to be your solid. You can also think about it in terms of the leaning of your lines. So a solid is going to be more dense than your liquid. So it leans on that because it's heavier, right? Your liquid is going to be more dense than your gas. So it leans on that because it's a little bit heavier. And if you go like this, it goes in reverse alphabetical order. So just a couple ways to remember it. Okay, so to answer question 2, what segment corresponds to the boiling point? A to B. Yep. Any point along this line is going to be the phase change. So depending on the temperature and depending on the pressure, that will change the boiling point. Any questions on 2? For number 3, we have determined the delta H for the reaction. We're given the overall reaction and we're given 2, I guess, intermediate steps or 2 broken down steps for our overall reaction. So what type of question is this? What do we call this? Yep, this is a Hess's law question. And what do we need to do in order to get to our overall reaction? Yep, we need to manipulate our equations. So someone tell me what we need to do.
In the end, the NOCl is become the reactant.
Good, awesome. So I heard both things that we need to do. So we need to flip both of these equations, right? NOCl here is in the root product, but we want it as a reactant. And then same thing for N2, we have it as a reactant here, but we need it as a product. So we're going to flip both of our equations. What does that do to the delta H? It changes the sign. What does it make it? Negative for the first one, positive for the second one. Okay, so we're going to flip this. Oops. And we're going to flip this. What else do we need to what else do we need to do? For which one? Both of them, right? We need this 1 half to go away for our N2, and we need a 2 in front of our NOCl. So we're going to multiply by 2 here. And if you wanted, I'll show you just show you what works. I'm not going to write the phases because I think you understand that. Hey, if we were to add these 2 equations together now, we see that our 2 NOs, one's a reactant, one's a product. Those will cancel out. What do we call that NO? What would that be considered? Catalyst. It would be a catalyst, right? You're going to first use it up and then produce it at the very end. Okay, so this would be 2 NOCl goes to N2 and O2 and Cl2. Which matches your top one here. So then you can just do the math for your delta H's. So I believe this becomes 186. Math in my head is Oh, sorry. I wrote a negative. Any questions? Yes.
What's the first one again?
Yep. So here, our N2 is a reactant, but we want it as a product. And so in order to get it as a product, we need to switch it.
So like the first equation, you're looking at like match. Or you're looking, yeah.
Yeah, so you're just looking to make sure that your reactants are on the reactant side and your products are on the product side.
Okay.
Right, so as long as you see, okay, I know N2 needs to be on the right, I'll flip that one.
Okay.
Yep. What other questions do we have? Feel good about Hess's law? Okay. So for 4, we have the highly exothermic reaction in which aluminum reduces iron 3 oxide to chemical or to elemental iron has been used by railroad repair crews to weld rail together. What mass of iron is formed if 496 kilojoules of heat is released? Do you want to do this together? You want to try it on your own? On your own? I can give you 3 minutes to do this on your own. All right, what answer did we get? Awesome. And now that I know you have the right answer, how did you do it?
Divided the delta H by 2, there was 2 moles of delta E.
Okay.
And then divided that or divided 496 got that answer. And that got me how many moles for one FE. And then multiply that by the molecular weights.
Awesome. Yep. So I'm gonna kind of show you how I would do it with like the railroad tracks. That's exactly correct. So we know from our delta H of reaction that 847.6 kilojoules are released for 2 moles of aluminum, for 1 mole of Fe2O3, for 2 moles of Fe, and for 1 mole of Al2O3. Right? It's always going to be that same stoichiometric ratio. If you have 2 moles of aluminum, this many moles of, or this many kilojoules of energy will be released. So we can say that we know that 496 kilojoules of energy are released. If it's released, that means it's negative. And we know that for every 2 moles of Fe, negative 847 kilojoules, or I guess 847.6 kilojoules are produced. Okay, and now we're in our favorite unit of moles. So now we can say that for every 1 mole of iron, we have 55.845 grams of iron. And then you can just do your math. Right, so now we're in our grams of iron. That mass matches the mass of iron that we're looking for. You should end up with 65.
What's the difference between the delta H of reaction or just the delta H?
Your delta H of reaction or the delta H. So the delta H of those are pretty much the same thing.
Right.
Your delta H might just apply to like the formation of aluminum or the, I guess, the formation of iron oxide. But the delta H of the reaction means, okay, this entire thing that you would form is going to release that. So like the overall delta H for it. Does this make sense for the math that you would solve for this one? Yes. Yes. This is just like stoichiometry with your delta H. So it's not necessarily a formula, but it's almost like the same process every time. You always want to use your stoichiometric ratio for like every 1 mole of this is the same as 2 moles of this, or 1 mole of that. So you could use the same thing here if you wanted to find the moles of aluminum. You could use the same ratio, you would just use a different mass. All right, any other questions on this one? Okay, so for number 5, we have what is the reaction order with respect to ClO2? Do you want to try this one on our own again, or yeah? Okay, I'll give you another 3 minutes and then we'll discuss. This is very similar to the first practice problem she had today that she didn't go over. It's like the first one in your slides.
Is there anyone else like between this? It's like Like. So like that, remember like order refers to the power. Did you know those? And the power determines how much is like the variable of the qualitative impacts. So A is. What to what extent? Yeah. Yeah, I don't know, but it's like, I guess it's easier, it's like. It's actually, maybe zero, if like, if you see the model, people would come to the receiving examples. If you don't feel like this is not a model, this is not a maybe zero, this is one. Because if I got like that, it's a finance. That's
Okay, what order is CLO2? Awesome. Okay, how do we do this one?
You trying to figure out the whole trial.
Awesome. Yep, and why'd you pick try one and trial two? Awesome. So whenever you're looking for the order in with respect to a certain reagent or a certain reactant, you always want to look for when that thing is changing, but everything else is held the same. So in trial 1 and 2, we see that this concentration is changing, but this concentration is being held the same. That means that whatever this rate changes by has to be due to the fact that our ClO2 concentration is changing. Yes.
So if the question isn't asking that, but if we were to find the order of OH, how would we do that? Because like if I'm getting like second, and you can't have like 2 second orders.
You can.
But you can. Oh.
Yeah. Yeah, there's no like rule against how many orders you can have. And we can also take a look at OH as well afterwards. So when we do ClO2, if you wanted to set it up in terms of a rate law, your rate would be equal to the K times your concentration of ClO2 to the M power times the concentration of OH minus to the N power. Okay. From our chart, we know concentration, we know rate. Okay, so we can say that our 8.0 times 10 to the negative 4 is equal to K times 0.024 to the M times 0.012 to the N. And you're going to divide that by the same rate law equation as trial 1. So you take 2.0 times 10 to the negative 4th over K 0.012 to the M and 0.012 to the N. Okay. You can cancel out your OH, you can cancel out your Ks, and you can combine your exponents for ClO2, and then you can do your math for the rate as well. So we get 4 equal to 2 to the M power. And so what value of N gets you to 4? 2. Okay, and if your power is 2, that means you have a second order. Right, if you get really good at this, you can say, okay, I see that my concentration is doubling. I see that my rate is quadrupling. That's going to be second order. But if you have really funky numbers, it might not be an exact double. And then you can set it up this way. And then you can see, right, it might be 1.9999 is equal to 2 to the M, right? And then you can say, okay, I know that that's about 2. So 2 equals 2 to the M, and has to be 1, like that.
Does it matter that you went from 8 to 2? Could you have done
You could have done 2 to 8. You could like trial 1 over trial 2. I just done a lot of these problems, so I game plan.
Okay, yeah.
So I say, okay, I'm gonna put my bigger number on top, so I end up with a whole number rather than a fraction.
Okay.
Yep. But you would still end up with 1/4 is equal to 1/2 to the m. You can still solve it the same way.
Okay.
I just think it's easier to see what times 2 gets me to 4 rather than what times 1/2 gets me to
Yes, yeah.
1/4. All right, if you were looking for the OH concentration or the order for OH, what trials would we look at? We would look at 1 and 3, right? We're gonna look at when this is changing, but your ClO2 is staying the same. So as you go from 2 to 4, what happens to your rate? It doubles. What happens when you go from 0.12 to 0.24? It also doubles. So if your rate is doubling while your concentration doubles, what's your order? You're going to be first order. Okay. So what would be the overall rate law for this reaction? It would be a third order, right? And your rate would be equal to K times ClO2 squared times OH minus.
What makes it a 0 order?
If this doubled and this still say 2, then your concentration changing has no effect on the rate. What's your units for K here? K has units. Capital K does not have units. This one definitely has units. That would be rate. So you know that your rate has to be molarity over second. How many molarities do you get from ClO2? Squared. How many molarities do you get from OH? You get 1, right? So we have right? So molarity over second is going to be equal to K times molar cubed. We're trying to solve for K or, X, right? We're going to divide by molar cubed. And so K is going to equal to 1 over molarity squared times seconds.
Change depending on the order of.
Yep. So K will have changing units. It'll always be some form of concentration per second, or I guess some form of concentration per time, right? It might be minutes, might be hours. But it'll always be some sort of concentration per time. And a good trick to remember, or to know the units of K is that it will always be 1 minus the overall rate order of your reaction, right? So the overall rate order was 3. So our unit on M is going to be 1 less than that. Right, so if we had a 4th order reaction, what's going to be our exponent on M? 3. If we had a 0 order reaction, what's going to be your exponent on M? -1. So what does that turn K into? It goes up top, and then it matches molarity per second. Yes.
So OH is the first order, but there's a 2 coefficient out front.
Yep.
Or we like talking about today, how like it's a coefficient out front 2.
So that only applies to your broken down steps. So if you know each elementary step of your reaction, then you can say the coefficient applies to the order. If you only know the overall reaction, we can't assume that.
So if we knew like the steps.
Yep. So that's like if you see like the slow, fast, fast, that sort of thing, then you can apply the coefficient to the rate. What is the rate determining step? The slow reaction. Awesome. Any other questions on 5? For 6, we have using the bond enthalpy table below. What is the delta H of reaction for the reaction below? So your enthalpy table is going to be on that question. But are we going to use this first delta H or the second delta H? Second, right? We're looking at bonds broken over bonds formed. Okay. So what I like to do is I always like to count how many of each bond I have. So how many CH bonds do I have on my reactant side? We have 4, right? We have this CH, this CH, this CH, this CH. So for bonds broken, that's gonna be 4 CH bonds broken. How many C double bonds broken? 1 C double bond, right? You can see that a CC bond is gonna be this much, but a C double bond is going to be this much, right? They count as different things. And then how many OH bonds do we have broken? 2. Awesome. Right, so we have 4 CH, 1 C double bond C, and 2 OHs. And what gets formed? How many CH bonds?
First one.
5. We have 5 CH bonds. How many CC bonds? 1 CC bond. How many COs? 1 CO. Anything else? 1 OH. Awesome.
How do you know they're broken?
So all reactants you can consider broken, all products you consider formed. So essentially it is products minus reactants again, but we have to look at each individual bond within our product and reactant.
Which one is the one where it's product or like it's reversed to that? This one's products minus reactants, which one's the one that's reacting?
I don't,
Is there one that's like that?
which one is it? Entropy?
There's one of the formulas. Probably minus H, right?
Not educated with the
I think most of them are,
right above the formula we used.
this is still products minus reactants though.
That's just a.
So there's not one.
Yeah, I don't think,
Okay.
yeah, I don't think she'll ask me react.
So if you're doing it, you know, like you see the picture, you know, it's bond broken versus bonds formed.
Yeah,
How's what is the problem with like this products minus reactant? Do they just give you like a product number and you do the reactant number?
yeah, so if it's that, I think there's one later on, like this one here, 14, they give you just a product, right? They don't give you the actual bonds here, they just give you the compound. Yes. Yes, I just looked at that again. This one is the one that is reactive
Reactive,
product,
okay.
it's broken minus forms.
Wait, isn't bond broken is the reactant?
Yep, so this is what I was, that's what was just asked. This one is technically reactants minus, products.
I was at the same as.
It is not. So this is for the whole compound. You're looking at just what it takes to form that. While this one is the bonds broken throughout all of the reactants. So sorry about that. This one is bonds broken minus bonds formed. So this one you just follow left to right. So all of these bonds are broken. All of these bonds are formed. And this one is going to be 34 kilojoules, negative 34 kilojoules.
So you just add those up.
Yep, so you could say, right, you have 4 times 413 plus 1 times 615 plus 2 times 463. All of that minus the sum of the ones formed.
I have a question.
Yep.
So on one of the quiz,
Mhm.
it's giving you C double bond, right? And then it's actual C single bond. How will you do that?
So you're given 2 different bond enthalpies, right?
No, they only give you C double bond. They don't give you C single bond.
Are you given a delta H of reaction? Yeah. So if you're given this and you say, okay, I want C double bond and I want to go to C single bond, you would be given the delta H is equal to 20 kilojoules. And so then you could say, okay, my 20 kilojoules is going to be equal to this bond enthalpy of whatever, 100, we'll say, for C, that's going to be broken, minus our one that's formed, and that's going to be your X. Okay, so you use that delta H in order to find that missing component. Question 14 of this mock exam does this with the products minus reactants equation, where you have to solve for X and you're given a delta H. Yes.
What's the difference between entropy and enthalpy?
So enthalpy is going to be heat, while entropy is disorder. So enthalpy is H, that's just the energy involved within the reaction, but then entropy is S, and that's molecular disorder. Yep. What other questions?
Do like less, like I can calculate a picture, so I cancel out like one's around.
Yep, so if you see that, like, okay, I know I have 4 on this side and 5 on this side, I'm just gonna use that one, right? You can definitely do that. Yeah, whatever you see fit for your algebra, like, and then you only have one OH. I think those are the only ones you can get. Any other questions? For question 7, we have, in which of the following situations is the reaction never spontaneous? So if something's to be spontaneous, what do we want that letter? Actually, let me ask a different question first. What letter determines spontaneity? Delta G. What do we want the letter to be if it's spontaneous? Negative. Right, if you can put in negative work and still get an A in chemistry, you would prefer that, right? The world prefers when you can put in negative work and still get the job done. Okay, for delta H, what does the world prefer in terms of its sign? Negative. Okay, we want things to be exothermic. We want energy, or we want heat to be put out into the universe. And what does the world prefer for delta H or for delta S? Awesome. Right, the world prefers disorder. It prefers chaos. So we want to increase that chaos at all times. Okay, so if something is negative for delta H, something is exothermic and increasing entropy, it'll always be spontaneous. So when will it never be spontaneous?
When H is positive.
Awesome, right? So that when it's the opposite, it'll never be spontaneous. So we want delta H positive and delta S negative. And what equation do we like to use for this one? Mhm. What is delta G when a reaction becomes spontaneous?
What's the question?
What is the value of delta G when the reaction becomes spontaneous?
Still be negative.
So delta G is 0 when a reaction becomes spontaneous. Okay, so if a question asks you at what temperature does a reaction become spontaneous, you can say delta G is 0, and you can solve for T if you're given delta H and delta S. Right, you might also be asked a question at 298 Kelvin, the reaction becomes spontaneous. What is the delta? What is the delta H? Right, you would be given delta S. You can say delta G is 0. You're given this portion of your equation, and you can solve for your delta H variable. Questions on that?
For that equation.
Yep.
The equation is temperature has to be Kelvin, right?
Yes. Yep. And then another important thing about units here, delta H is usually in kilojoules, delta S is usually in joules. So you do have to change one of your units. Oftentimes I change my delta S to kilojoules, and then switch back to kilojoules at the very end. Or then it just comes out in Kelvin if you're solving the temperature. But do note that those are usually different units. What other questions do we have? Say that again. Yep, so delta H is usually in kilojoules, and then delta S is usually in joules. Yep. Any other questions? Question 8. We have the elementary steps for the formation of nitrogen and water from nitrogen or from nitrogen oxide and hydrogen are given below. What is the overall rate law for this reaction? Which one's the rate determining step? This is our rate determining step. And so now here we're able to use our coefficients because we're given each elementary step. Okay. So what's going to be the rate law? And YA. Awesome. Right. So our slow step determines our rate. So we know that rate will be equal to K times any reactants you may have. We just have one. And then the coefficient becomes its order. So that's going to be 2. What is N2O2 considered here? What would we call that?
Intermediate.
That'll be an intermediate.
On the reactant first, and it's catalyst.
Yep. So do we have any catalysts in this one? Nope, no catalyst here, right? We see that NO gets used up and we don't see it anywhere else within our equations. So no catalysts. But N2O2 is going to be a intermediate. And N2O, it will be also an intermediate.
And so what makes it intermediate, just that it's used in one and then used again in another?
As long as if it's produced and then consumed, it'll be an intermediate.
And the rate will always be the left side of the equation whenever it's like this.
Yep. I don't think she will give you a second like step at your slow reaction. But you cannot have any intermediates in your rate law.
But a catalyst would be.
The catalyst can be, yep.
Wait, does it have to start at the beginning, like where it could start like the second step?
Yeah, so N2O would be an intermediate here. Right, because it's first produced and then consumed.
And what is a catalyst again?
Catalyst would be consumed and then produced. So that's like if we had, I don't know, iron here and then iron on the very end. I don't know why that would be there, right? But it's going to be a reactant and then a product. Yep.
So it can't, there's the, I think it's like, in the second equation.
If it was in the second equation and then still produced, then it could still be a catalyst. Yep. It just has to be consumed first and then produced again.
What do we do if she gives us an intermediate on the left side, or she is wrong?
You have to do some fun math. If we have time at the very end, I'll show you what to do if your slow step is second. Has anyone seen a question with a slow step second? I don't think she's going to ask you that. But if you're really curious, I'll show you what you have to do. Any other questions on slow steps, rate laws, fun stuff like that? Yes. Good. High fives. Awesome. Number 9. How much energy is required to heat 87.1 grams of acetone from a solid at negative 154 degrees Celsius to a liquid at 42.0 degrees Celsius? Yeah. How many formulas do we need here? 2. What 2 formulas are you going to use? So we're going to use our 2 formulas. We're going to have MC delta T and N delta H diffusion. Does anyone know how many times we need to use each one?
One is for the first, one was for the second.
Yeah, awesome. So whenever I see a question like this, does anyone like know what we're using? What kind of graph we're using?
It's like really.
Yep, phase change graph or a melting curve is what we call it, I believe. So that's when it's your stepwise function like this. Okay, so I always tend to draw these when I am on an exam, if I'm doing one of these questions. And I usually like to draw my path that I'm taking. So I know I'm starting at a solid, so I'm on this bottom portion here. And I have to go to a liquid, someplace here. So I have to go from my phase change through the phase change and then up to my temperature at a liquid. So I have 3 different segments I need to follow. So that means I need 3 different terms in my Q. Okay, another thing to note is that your delta H of fusion is in kilojoules per mole. So that means you need to take your grams of acetone and change that into moles. That also means you need to change your kilojoules to joules, since your other stuff is in joules. You can also take your joules and convert them to kilojoules. But everything else is in joules. I would do it in joules. Do we need to change our temperature? Nope. Everything here is going to be in degrees Celsius, so you can keep your degrees Celsius, no problem. Okay, so we can say that we have Q is equal to our mass, which is 87.1 grams. What delta C or what C do we use first? Solid, so that's be 1.65 joules per gram per degree Celsius. And what's going to be our first delta T?
Cold. Or liquid.
What values are you going to use for your first delta T?
Because minus 95, negative 95,
Why do you say 95?
because that's the melting point.
Good. So you can't go directly from negative 154 to 42 or to negative 42. You have to stop at your melting point, right? You have to get to your melting, go through the melting, and then you can go back up and then you can use your next one. So your first one's going to be final minus initial. So it'll be negative 95 minus negative 154. And that takes care of your first MC delta T component. Questions? You're doing, delta T will always be final minus initial. So you're starting at 154 and have to get to 95. Okay, your next is going to be the N times delta H of fusion. So that N stands for number of moles. I believe this is 1.5 if I'm doing mental math correctly. So it's 1.5 moles, and we got that just by using our molar mass in our grams. And then we have our delta H of fusion, which would be 7270 joules over mole.
Are you adding that?
This is going to be a plus. So all of this, right, all 3 components here is going to equal the overall heat that's required.
Which formula was that that combined them?
That's just saying that the Q for this segment here costs this much. The Q for this segment here costs this much, and the Q for the next segment will add up to the overall Q.
Okay.
Yep. So you can find the Q of each individual step, but you need the total energy, so that's just why we add them. Okay, and then your MC delta T will look very similar to the first portion. It's still at 87.1. We didn't lose any along the way. This time we use our heat of our specific heat of liquid. So we're just going to do the 2.16. And then this time our delta T is going to be negative 42 minus negative 95. And we end up with your 29.4 kilojoules at the very end. after you do this, add it to this, add it to this. Questions? This one?
Yeah.
Because your joules here and joules here, and so since you need to find the total, you need them all to be in the same units.
Does it, is they, you're gonna pop out in joules? and
Yes.
convert back to joules?
Yep, so the answer will pop out in joules and you'll just convert it back to joules or to kilojoules. So you should have a pretty big number and then can move your decimal point. Yes,
So why did you only like, how do you know how many times to add the fusion back? Like that time we added like Q twice, but like what if we had to add the fusion again? How do you know?
so it depends on how many phase changes you're going through.
Okay.
So we're only melting this, right? Because we're going from solid to liquid, so we only go through one phase change. If we needed to get to gas, then we would go through this other phase change here.
So for every phase change, there should be like 3 or so, like, or like 3 and then 5 and then 7.
It depends.
Depends.
And right, like if you wanted to fully boil, then you would only have 4, right? To fully boil, you're gonna get through your entire phase change.
Mhm.
If you wanted to get higher into your temperature for your gas, then you would have one more segment that you need to get to. So it all just depends on where you fall on that melting curve that we see here.
But for the exam, we can probably just assume it'll be set up like this. like
Yeah,
3.
yeah, probably 3. It might be liquid to gas. But it would still be like 3 phase changes. Okay, you just want to look at the temperature you're starting, how many, what, if you have to go through a phase change, and then what temperature you end up. Right, if we stopped at 95, we don't need that last MC delta T, because then we're at 95. Any other questions? Okay, question 10. For which process is delta S negative? So for A, we have compressing 1 mole of neon at constant temperature from 1.5 liters to 0.5 liters. What does volume change due to, or a decrease in volume due to entropy?
Wouldn't make it more compressed, so it wouldn't be all over.
Yep, and so is that going to increase or decrease disorder?
Decrease.
And for decrease in disorder, right? So this will have a decrease in disorder. So what does that mean for delta S? That would be negative. Okay, and I am paranoid, so I always check to make sure that my other answers are positive. So for evaporating 1 mole of CCl4, what are we doing? Good. We're going from liquid to gas, which is going to increase delta S. Right, anytime you make gas, you are creating more entropy. If you're mixing 5 mils of ethanol with 25 mils of water, what happens? You're increasing your volume, you're putting more things into solution, you're creating more disorder. This also has a positive delta S. This was an increase in volume. And then we're raising the temperature of 100 grams of copper from 275 Kelvin to 295 Kelvin. Yeah, awesome. Anytime you increase temperature, you're always increasing disorder. You're always getting towards that gaseous phase a little bit closer, or you're just increasing the heat of your gas a little bit more. Yeah.
If you weren't, or C, if you weren't mixing anything and you're just increasing the volume, does that increase disorder?
Yep, it also does. Anytime you're going to just increase your volume should increase the number of disordered stuff you have. Because that's also, right, if you were just adding 5 more mils of water, that's just more molecules of water interacting. Question?
Can you explain why it's A again? Because
Yep. So if we are compressing 1 mole of neon at constant pressure from 1.5 liters to 0.5 liters, we have a decrease in volume, right? So that's saying we're taking all the gases in a basketball and shrinking it down to all of the gases in the golf ball, right? So those gases are now not have as much space to move in their container. And since they don't have as much space to move, that's less disorder, right? Instead of bouncing between these walls, they're bouncing between my hands, right? And that's less disorder.
Okay, I just thought it would be more because they're kind of colliding with each other more frequently than, right?
Yes, but if you increase your pressure, it starts making more solid, like, right? The air within a golf ball is very tight. It's not a lot of stuff in there, but the air inside a basketball is very big, right? So the more pressure you have, the more solid like tendencies it has. And solids always have less disorder than gases. Does that make sense? Okay. Yep.
Could you explain what it means by disorder?
So disorder is always going to be molecular motion. So molecular motion is just how quickly molecules are moving. So gases have free range, right? Low intermolecular forces. They're always going to be bouncing fast. But solids are stationary, right? This does not have a lot of disorder, but the air in the room has a lot of disorder,
Okay.
right? So entropy disorder just means molecular motion.
Okay.
Yep. Any other questions on delta S? Okay, for number 11, we have identified all of the intermolecular forces or IMF present between the molecules in a pure sample of a compound below. Yep, so LDF or London dispersion forces will be in every single molecule you see. So it's always going to be LDF. If I see you not picking LDF, I will be very upset. What else do we have? Why do we have dipole? It's not symmetric. Can anyone tell me where we have a polar bond? Awesome. So, and which is going to be more electronegative? Oxygen. Awesome. Right, so you have a dipole here where your oxygen is going to be pulling your electrons more than your carbon. And that'll inherently make everything else polar in that molecule as well. But as long as you have one polar molecule or one polar bond, you will have dipole-dipole interaction. So on the periodic table, your this is sideways, but your electronegativity increases as you go from left to right, which in this case is bottom to top. So fluorine is the most electronegative. So oxygen, carbon, nitrogen. Oxygen is going to be more electronegative than carbon.
Yeah, but if they're close, they're close enough that it's not electric.
This is not close enough. In this case, it's not close enough. You can assume that this trend here will create some sort of dipole. Any carbon to fluorine, carbon to nitrogen, carbon to oxygen, those will all be a polar bond. N to F would have a polar bond. O to F would have a polar bond.
Couldn't you just base it off of molecular geometry, like the picture?
Yep, and then you can also do molecular geometry. But in terms of these four here, anyone attached to any of them will have a polar bond. F has an electronegativity of 4. I believe oxygen has an electronegativity of 3.6. So 0.4 is going to be enough to make a polar bond.
The only one that had a non-polar bond was CH, right?
Yep, CH is the only non-polar bond. And then anything that's like C and C, that will not have a polar bond. Yep, so ion dipole would not happen in this case because you're in a pure sample. That means you only have these here. In order to have an ion dipole, you need some sort of ion. So we'll call it sodium here. And then you need a polar substance. So we'll call it CF.
So you would be able to see the ion.
Yep, you would see the ion. Yep. They would tell you an ion is present, and then you would have an ion.
Like, was there ever pictures where it's like in brackets, like -1? Or no?
That could also be a case, right? You could have a polyatomic ion if you have PO4 3-, right? We have a ion here. These have a full charge, and so this could create an ion dipole.
They'll draw the charge on there like the.
Yep, they'll tell you it's it. Yep.
If it's not polar, it's just
Yep. If it's non-polar, it's just London dispersion. Why do we not have hydrogen bonds here?
That has to be OH, NH, or FH.
Awesome. Right, we need an O attached, or we need an H attached to a hydrogen, or wow, a nitrogen, oxygen, or fluorine. So it needs to directly be one of those three in order to be hydrogen bonding. We also have dipole dipole here. Right, and we said that in the other, these will always be polar bonds. And then hydrogen and carbon have the same electronegativity. So if you plug in carbon here, those will also be polar bonds. Yes.
What's one where it's like something induced dipole? What causes that?
So if you have a something induced dipole, it will never be with a pure substance.
Okay.
So if you see pure substance, you don't need to worry about it. But if it is an induced dipole, that means you have a non-polar substance. So something like carbon-carbon. And then if you bring, right, if you just have a carbon-carbon floating around, and then you bring an ion close by, that'll cause your electrons that are negatively charged to be attracted to that positive charge. So in that brief instant where that ion is close, it causes a dipole in a nonpolar substance. But if you removed that ion, then it would go back to its nonpolar situation. Okay.
Thank you.
Yep.
Yes.
Any other questions? Okay. Stick around till 6:30, finishing our exam, yeah? Y'all are troopers. This will be longer than what you have to do on Monday or on Friday, so. Okay, for number 12, we have for a given reaction, the activation energy, EA, is 29.1 kilojoules per mole. If the reaction rate constant K1 is 8.12 times 10 to the whatever, at 298 Kelvin, what is the reaction rate constant at 318 Kelvin? Yep, so this is just your formula. So this is what we talked about on this last equation here. Right? We have two different rate constants, we have two temperatures. We don't know a rate constant, so we're going to solve for that in our equation. The important thing to note here is that K2 is T2 second, and then K1 is T1 first. Okay, so this is the ln of K2 over K1 is equal to EA over R times 1 over T1, oops, minus 1 over T2. What R do we use in this case? Awesome. And why do we use that one? And constants, yeah. So our units on this one is joules, which is great for energy, times mole times Kelvin. Yes, so that's on up here. So it should be right. Alrighty, so we know K1, we don't know K2. And then our temperatures are already in Kelvin, so that's nice. So we can just plug in what we know. So we have ln, I'm going to say of X. And then I'm just going to keep K1 for right now because I don't want to write that out a whole bunch of times. This is just going to be K1 and I'll fill it in later. And then we have 29. What do we notice about our units here and our units here? Yep. So let's change this to joules. Which one is T1? Good. All right, this is like not legible at all. Okay, so I would solve this side first to get a whole number before you do your natural log. Then I'm gonna get a value for that right side. How do we get rid of a natural log? Awesome. Now to get rid of my natural log, I'll put it in my 8.12 times 10.4. Now you can cross multiply, isolate x. And so x or so k2 equal 1.70 times 10 to the negative 3. 1/meters times seconds. Yes.
We would have to include units, right?
Mhm.
We would?
Yep.
But they'd already be on the test for us, so like we don't like write the units out.
It might have you fill in the blank or something. I don't know. Might be like a box fraction kind of thing. But it should match whatever K1 is. So should just work out. But I don't take your test, so I'm not exactly sure.
You should have said something.
I take all of your mock exams, so that's something, right? Any questions on 12? I will say last year for the final, she gave a mock final and I spent an entire Zoom just doing it myself. So yes. And I can post all of my stuff too. Okay. So for 13, we had given that the reaction below delta H is this and delta S is that. Determine the range of temperatures at which the reaction is spontaneous. What do we need to do for this one?
You're solving for T.
Yep, we're solving for T. So we need to know the range at which delta H is spontaneous and delta H is not spontaneous, or delta G is not spontaneous. So what do we say when a reaction becomes spontaneous? What is delta G? Delta G is 0. Okay, so we're using delta G equal to delta H minus T delta S. What do we need to change for delta S and delta H?
What
Good. So we have 442. Delta H is in kilojoules, so we'll change that to joules. 400 joules. Minus T is our unknown. And we have 206.9 joules per Kelvin. We can then say that T times 206.9 joules per Kelvin is equal to 442 joules. And how do we solve for T? Yep, you divide by 206. And T will be equal to some positive number. Do you know what that some positive number is?
$2,138.
And what units is that in? Good. It's in Kelvin. Okay, so what is your answer going to look like?
Is greater than or equal to that number?
Yes, so T should be greater than 2138. Oops.
So if it's equal to 0, it's not spontaneous or the other one.
Right,
Okay.
right. So we want greater than 2138. This is when it becomes spontaneous. We need just a little bit more than this value here. Okay, when we look at this whole equation here, we have delta G is equal to delta H minus T delta S. So when you have a positive and a positive, you want this negative component to be more negative than this positive answer here. So you want really, really high temperatures in order to make this portion of the equation more negative than the positive. So the higher the temperature, the more negative delta G becomes. That makes sense. Why that's happening. So if you had a negative delta H and a negative delta S, when would you like what range would you like your temperature to be? Lower, right? So we want lower temperatures because then our delta H component still is more negative than the positive component. Any questions on 13?
If it's spontaneous, G is positive.
G is negative.
Negative.
Yep. Right, the least amount of effort for the best bang for your buck. Okay, 14. Using the enthalpy of formation table to the right and delta H of reaction for the reaction below, calculate delta H of formation for PBO solid and kilojoules per mole, and report your answer to the nearest whole number in the box. Okay, so we did one for the bonds broken, bonds formed. So I'll give you a second to try this one on your own.
Also related to there's like a two in front of EV or not EV, this CO2. Would you multiply 393.5 by 2?
Yes. Yep.
Well, I have something like that. It's been less bright, so that
Okay, so you're using your sum of the products minus the sum of the reactants. You're given delta H, that's similar to like that question we had earlier. And we're solving for X, which is your CO, or I'm sorry, your PBO solid. Does anyone tell me why PB solid is 0? Yep, it's in its elemental state, naturally how it occurs. So it takes no effort to form something in its elemental state. Okay, I always like to write this out first because this negative needs to distribute to both your X and your negative 110. So this ends up as negative 131.4 minus 393.5 minus X plus 110.5. Okay, X is by itself. And so you can just solve for X, and X will end up as negative 152 kilojoules per mole. Questions on how we got there? Okay, last question. So we have when 0.025 moles of HCl is added to 0.025 moles of NaOH in a coffee cup calorimeter, the temperature of 100 grams solution increases by 3.2 degrees Celsius. Calorimeter has a heat capacity of 433 joules per Celsius. We want to know what the heat of the reaction per mole of acid, or delta H, for this reaction. We can say that the solution for the specific heat has the same as water.
Yeah.
And how are we going to do this one? So we know that the Q of the reaction will be Q water plus Q cal. What is Q water? MC delta T. What is Q cal? C cal times delta T. I believe so. Yes.
So what you mean is using negative Q.
Say it again.
That thing has to be negative Q, it's now positive.
Negative Q reaction.
Yeah, negative Q reaction.
Yes. Yep, because the Q of the solution will equal the negative Q of the reaction. Yep. So we could say negative Q reaction. Okay, and then how do we do MC delta T? Mm-hmm. 100 grams. Delta T. Mm-hmm. What's C cal? Mm-hmm. What's delta T? Awesome. Yeah, so they're saying that the specific heat has the same capacity as water. Okay, and what do we get for this value? Remember this Q, negative Q reaction. If you want to cue the reaction, you divide by negative at the very end.
Negative 2,724.
I think you get 2,000. Yeah, negative 2,724. So then Q reaction is negative 27. And what units is this in? Joules. So how do we get it in kilojoules per mole? We're going to divide by 1,000 to get to kilojoules. And how do we get that mole component? Per mole of what? Which one's your acid? Right, so how many moles do we want? 0.025, right? So we have 0.025 mole of HCl.
Why are we dividing by 0.025?
Because we're just looking for the per mole of acid. So even though you have this acid in this base, we just want the acid
Oh.
component. And what do we get for delta H reaction? Do we want a negative or do we want a positive?
Make sure they include negative 5.
Do we want a negative or a positive?
No. Oh, positive because it's absorbing heat now. Or is it the calorie?
We're looking for the reaction delta H.
Oh, negative. because it's-
Negative, yep. So your solution, your calorimeter, the temperature of the solution is increasing by 3.2. Right, so that means your surroundings increasing by 3.2. In order to increase, something had to be released. And so that means the reaction actually happening is exothermic. And since it's exothermic, we need to indicate that with our negative 109.
That would be the reaction, everything else would be like the solution. I
Yep,
guess.
yep.
Okay, solution and surroundings are the same.
Okay, that is the end of the mock exam. If anyone has any specific questions, you're free to ask them. If not, when you're tired, let me know. What's up?
Just roll back up to the first page, so I can type my answers.
Yeah.
I have a question on one of the.
Yes.
Answer the solution. They review it all again.
Yep, yeah, I'll post all this. I know Dr. Alphonse has just the answer key up, but I'll put like my stuff on it as well. Yep, and then I also have been Zoom recording this, so I'll upload that as well.
Thank you.
You had a question?
Sorry, I didn't have a question. Can I put one of the homework?
Yeah.
I cannot figure out what I'm doing on here. I thought I understood how to do it, but I don't know. So, this one right here. We had,
He's just checking his answer, and then I'll do that. Oh, yeah.
on this one right here, I thought, because we had our slow and fast step reactions. So I thought, I was like, okay, like, I thought it would have had two on the outside. Because we have, two here, so. But then this one, we had two right here, and it didn't want to have. As,
Okay, so this is your overall reaction. You can only base your coefficient on the order for your elements.
Oh.
So in this equation here, right, you have H2 and ICO, no two in front of each other, that's why your base is this.
Okay, and
Right,
then this
and then
one.
the other one, they have two. Yeah.
Thank you.
So besides this,
Yeah.
are you like doing anything else?
If you need me to do anything else, I can do that.
Did you say you're gonna do like something or like a Zoom?
Yeah, I can do something tomorrow night if y'all want it. You can ask some questions.
Well, I was just wondering, I'm not like
Yeah,
asking for
I mean,
anything, I'm
it's-
just, if
I-
we're gonna do anything.
Trying to do something over the weekend, but then my weekend plans kind of got screwed up. My boss asked for something Friday, so I had to kind of do that this weekend.
Right.
But if y'all need anything, any extra practice questions the day before, I can do that as well.
Okay.
If that's something interesting, if you just want me to sit on a Zoom for an hour tomorrow and you can ask me questions, I can also do that.
Okay. Alright. well,
Yeah,
thank you.
yeah, let me know if you need.
You didn't do a practice, did you? Or no?
I didn't do like practice questions, but I can put something together tonight or tomorrow morning real quick, and then you can have that to practice last minute tomorrow. If that's helpful.
Yeah, because your questions were hard.
Okay,
So like, but they're actually like, let's mix other stuff.
I mean, I can do that for y'all if you would like. Yeah,
If you
Okay.
could, that'd be awesome.
yeah, absolutely.
Yeah,
Yep.
fine.
Yes.
So I took a picture of not 13, 14, sorry. So I was trying to write down 13 and I took a picture of it and it was 14.
Sorry.
Another question on the homework. So, can you walk me through what we would do to go about this question?
Yeah. So. Okay, so that's going to be very similar to question 12 that we did today. So, right, we have 3 different rate equations and we have different temperatures. So here we're looking for the activation energy, which is this EA. So you can pick any 2 rates, any 2 Ks, and then any 2 temperatures as long as they stay the same, right? So if you pick this 2.0, you want to pick the 2.5.
Okay,
Okay, if you pick 1.4, you want to pick the 4.
okay,
That doesn't matter.
Oh yeah, that one was annoying.
So then what you have to do is,
It's an equation. You plug all
yeah,
this
so then you
stuff
can
in.
just plug and chug after that essentially.
okay, okay.
So then you can like use that or whatever. You can also plug this into Excel.
Because, okay, that's what I think they were doing, and I was
Yeah.
trying to
There's
understand.
a separate way, flow. There's like 2, I don't know why, it just occurred, I was reading, it's like, actually, there's 2 ways to do it.
Oh, this is the one that. we
Yeah.
were-
Yeah, that one.
Okay, so then, okay.
Yeah, so like,
That's what we did actually.
yes, this is what
Okay.
you do. This is what, how I would see it is that you like use your 2 Ks, use your 2 temperatures, you have R, solve for the unknown of EA.
Okay.
Right, you don't have Excel in the exam for your homework to do that, then you just find the equation as a line. But for this, I would probably.
Okay, and then we can use either one for K1 and K2 as long as it's
Yep,
consistent.
as long as they're the same, and then, so it's like K2 which matches P1, and then K1 which matches.
Okay, thank you. And then there was something else where it's like we had the concentration over, or it's like negative concentration over delta. Like one of these things.
Yep.
So is this, which one is it the moles of?
That would be, right, if you have,
I can't remember the name of that formula, but
it's not, I don't really think it has a name, but it's just like your rate of reaction.
okay.
So if you have like 2A plus B goes to products, then your rate would be 1/2
Okay.
times the concentration of A over T, right?
Okay, yes, yeah.
Yep, so then it's like this becomes your reciprocal
Okay.
in your rate.
But if you had like A plus B to C, what would you do with that?
Yep, so then that's still the same thing. This would be negative delta concentration of A over delta T plus equals the negative delta concentration of B over delta D. And then same thing here, this still becomes 1/2. But this one's a positive C because you're producing products. And so your rate of product formation will always be positive.
Okay. So no matter what, if there's a coefficient, no matter where it is, it's always going to be on the denominator.
Yes.
Essentially.
Yep, right. But if it's like 1/2, then it would be.
Okay. Okay, so you said that this one, if it were one of these ones, it would be positive.
For the products.
Okay. Because you're producing more of it.
Yep, you're
versus-
producing products where your reactants are getting used up. So it's negative.
Oh, because here, this one is getting used up. And
Yep.
then it goes, oh, okay, that makes sense. Thank you.
Yes, of course.
This was so helpful. Thank
Okay,
you so much.
awesome.
Have a list of like all the lab TAs like email.
I do not. Do you know who your lab TA is?
Yeah, Shenwan.
It might be in,
I think I can, you know how sometimes when you like look something up, it kind of like autofills?
yeah, it might come up there if you look on like Gmail and stuff. Worst case scenario, email the IAs and they can probably get it to you.
Okay.
Yeah.
I talked to Dr. Altimos today because my lab group, like, her project.
Yeah.
and no one's like working on it. And then like finally, like someone did do something.
Okay.
but The thing is like, it's due tonight.
Yeah,
Whatever, and she said she would send me data, but she hasn't, and I know she's notorious for emailing late.
okay.
So do I just like go with the flow?
Did you email her or ask her in person?
I both. I asked her in person and then I said, or she said, email me. So I said that. So I emailed her right after.
Okay. You can also just send her up a follow-up, be like, hey, I know, I'm sorry to like bug you again. It's just due tonight.
Okay.
Words.
Just want to make sure like you still saw this or something like that, right? Yeah.
Yeah.
Because you might have just missed your email
Yeah.
after class and then, things happen. So I would just send her a follow-up. Yeah.
Okay, thank you. so
Yep,
much.
of course.
Or like remember example that there were two things that had to be like that we chose to like type out